If we have some sample of liquid water and we add heat to it, we know the temperature is going to increase. If we remove heat from it, we know the temperature will decrease. And the relationship between those we know is Q equals mc delta T. So this is what we have when we have some kind of temperature change with the material. But what happens if we take out so much energy that the temperature of the water gets to 0 degrees? If we continue to remove energy from it, the liquid water starts turning into solid water. It starts to change into ice. But we continue to have to remove energy from it to make that change. To go from a liquid to a solid requires the removal of energy even without a temperature change. The relationship between the amount of energy that is needed to be removed, or the other way around, to put it back in to make the solid go to a liquid, is related again to the amount of material we have, and it's related to the material. In this case, we have a relationship where Q equals mL, where L is referred to as the latent heat. And the value of L not only depends on the material, but it also depends on what the change is, what material what form of the material. We call that a phase. So there's the liquid phase, the solid phase, or the gaseous phase. And when the material goes from one to the other, we call that a phase change. So when our material has a temperature change, we use Q equals mc delta T. When our material has a phase change, we use Q equals mL. Now I'll come back to the different values of latent heat in just a second. But what kind of phase changes can we have? Well, if we have a solid going into a liquid, turning into a liquid, we usually refer to that as melting. If the liquid is going into a solid, we call that freezing. So you can have an ice cube that melts, or you can have water that freezes into ice. If you have a liquid that is turning into a gas, we refer to that as either boiling or vaporization. If the gas is then coming back into the liquid form, we call that condensing or condensation. It is possible that a solid can go directly into a gas without going through the liquid phase intermediately, so to speak. It goes right directly from a solid to a gas. There's a very, very common material that does this. You might be familiar with it. If you've ever heard about dry ice is frozen carbon dioxide. And if you have a block of dry ice, it doesn't melt into liquid carbon dioxide and then into gaseous carbon dioxide. It goes directly from solid carbon dioxide to gaseous carbon dioxide. This actually happens with water sometimes as well. If you've ever noticed, if you've got like an ice cube tray or just ice in your freezer, if you leave it for long enough, you come back, the ice seems to have gotten smaller. Well, that's actually what happened. The ice is turning into gaseous water very slowly, but that's what's happening. It's turning into water vapor directly from a solid to a gas without melting first. When the solid turns into a gas, we call that sublimation. If the gas turns back into the solid, we call that nucleation. For us, for the calculations that we're going to do, I'm primarily interested in this change right here. This way, solid, liquid, liquid to gas, but really even primarily between these right here. If I could get my students to be able to do calculations just between these two, I'd be happy enough. Okay, so we're going to focus on these. But I want to put some numbers in that's going to include a change all the way up to the gas. So let's imagine that we've got a sample of, let's say, solid water, in other words, ice, and we want to figure out how much energy do we have to turn it into, do we have to add to it to turn it into a gas. Let's take a look at that. Let's imagine that we've got 2.50 kilograms of water at negative 10 degrees centigrade. So what kind of water is this? If it's at negative 10 degrees centigrade, it's below 0 degrees, it has to be ice. So we've got 2.50 kilograms of water ice at negative 10 degrees centigrade. And we want to turn this into steam, gaseous water, water vapor, at 100 degrees centigrade. We're going to do this by adding energy to it. How is that going to happen? What steps, so to speak, do we have to go through? We start out with the ice at negative 10 degrees centigrade. We start adding energy into it. what's going to happen? Well, the ice doesn't melt yet because ice won't melt until it's at 0 degrees centigrade. So the first thing we have to do is we have to get it up to 0 degrees centigrade. So we're going to heat the ice to 0 degrees centigrade. In other words, we're going to have a temperature change. We'll call this amount of energy, we'll call this Q1. Then what happens? We've got ice at 0 degrees centigrade, 0 degrees Celsius. We continue to add energy into it. What's going to happen? Well, the ice will start to melt. So we keep adding energy until all of the ice melts, and then we've got 2.5 kilograms of liquid water. So the next step we have to go through is to melt the ice at 0 degrees centigrade. So there's not going to be a temperature change as we melt the ice. We're going to start out with ice at 0 degrees centigrade, and we're going to end up Celsius, and we're going to end up with liquid water at 0 degrees Celsius. No temperature change, only a phase change. We'll call this energy Q2. Then we start out with liquid water at 0 degrees centigrade. We keep adding energy into it. What's going to happen? Then the water is going to start to heat up. So the water will heat up until it gets to 100 degrees centigrade. Celsius, sorry. So we're going to heat the water. And we'll heat the water from 0 degrees Celsius to 100 degrees Celsius. And we'll call that energy Q3. And then what? Once the water gets to 100 degrees Celsius, we keep adding energy into it. What is it going to do? Then it's going to turn into water vapor or steam at 100 degrees Celsius. So then we will boil the water or vaporize the water at 100 degrees Celsius. And notice, the water goes from liquid at 100 degrees to steam at 100 degrees. Again, we have no temperature change. This is only the energy due to the phase change. We'll call this Q4. Now let's figure out what these values are. And I'll give you the constants that we need as we go along. So we heat the ice, I should have put down, from -10 degrees to 0 degrees. What is that? A temperature change. So Q1 will equal MC delta T. What's the mass? Well, the mass is just the mass of the water, 2.50 kilograms, times the specific heat. Now, what specific heat do we use here? We don't have liquid water, we've got solid water, we've got ice. So we need the specific heat of ice, which is actually different than the specific heat of liquid water. It is 2.00 times 10 to the third joules per kilogram degree Celsius. Times delta T. So what's the temperature change for the ice? It's going from -10 to 0, that's a change of 10 degrees Celsius. So times 10 degrees Celsius. And what do we get? We multiply that out and we get 5.00 times 10 to the fourth joules. Okay, so that's Q1. Next step, we're going to melt the ice at 0 degrees. That is a phase change. We ask ourselves, are we talking about a temperature change or a phase change? This is a phase change. So Q2 equals ML. Now, what phase are we talking about? We're going from a solid to a liquid phase. The latent heat that we use for that is called L sub V. That's called the latent heat of vaporization. So I'll write it up here. LV is the latent heat of vaporization. I'm sorry, that is not correct. The latent heat that we use here is called L sub F. That's the latent heat of fusion. So L sub F is called the latent heat of fusion. So fusion, thinking about liquid to a solid, it's fusing together. So the liquid solid or solid liquid phase change, either way, we use the latent heat of fusion. So what's this? Well, this will be the mass, again, same mass, 2.50 kilograms, times the latent heat of fusion of water is 3.35 times 10 to the 5th joules per kilogram. There's no degrees Celsius in the latent heat because there's no temperature change that we need to cancel out. Just joules per kilogram. These cancel out, multiply that, and what do we get? We get 8.38 times 10 to the 5th joules. And there is Q2. Next step, Q3. What are we doing? We're heating water from 0 to 100 degrees. So is that a temperature change or a phase change? That's a temperature change. So Q3 equals MC delta T. M, again, 2.50 kilograms, times C. Now we're talking about the specific heat of water. We've got liquid water for this entire change. So 4186 joules per kilogram degrees Celsius times delta T. What's delta T? We're going from 0 to 100 degrees, so delta T is 100 degrees. And multiply that out, and what do we get? We get 1.05 times 10 to the 6th joules. There we go. Okay, last step, Q4. We're going to boil the water at 100 degrees. So we're changing liquid water at 100 to steam at 100. Is that a temperature change or a phase change? That's a phase change, so this will be L. And the latent heat that we use in this case is called L sub V, or the latent heat of vaporization. Vaporization, we're going into a vapor. We're turning the liquid into a vapor. There is a latent heat of sublimation, which is the solid to gas phase change, but like I said, we're not going to worry about that one. We'll just stick with these for now, for us anyways. So L sub V, latent heat of vaporization. Okay, there we go. Which is then the mass, again, same mass, 2.50 kilograms, times the latent heat of vaporization for water is 2.26, 2.26 times 10 to the 6th joules per kilogram. Multiply that out, and what do we get? We get 5.65 times 10 to the 6th joules. There we go. How much energy do we have to add all together? Well, we add these up, but before we do that, I just want us to notice one thing that's interesting, and that is that these numbers are just getting bigger and bigger and bigger. We've got 5 times 10 to the 4th, 8 times 10 to the 5th, 1 times 10 to the 6th, 5 times 10 to the 6th. Now, this one is small because of the temperature at which we started the ice. If we had started it much, much colder, this would be much, much larger. But anyways, for this particular temperature change, we notice that the energies increase. The steam, changing the 100 degree water to 100 degree steam, requires the most amount of energy. And this tells us, kind of explains why steam can burn you so easily. If you accidentally put your hand, say, in front of a teapot that's spewing steam out, you can get burned very quickly. And that is because when that steam hits your hand and the steam condenses back into a liquid, it gives up a substantial amount of energy. And where does that energy go? It goes into your hand. A lot of it goes into your hand, and so you have a lot of energy going right into your hand. That's going to burn you. So this kind of explains why it's so easy for steam, or for you to get burned by steam, because steam has got so much energy in it. All right, so we add these together, and what's the total? It is 7.59 times 10 to the 6th joules. So that's the amount of energy that we would have to add to 2.5 kilograms of ice at negative 10 degrees centigrade and turn it into steam at 2.5 kilograms of steam at 100 degrees centigrade. Okay, very, very good. I want to take a look at another mixture problem, and I'll warn you that many students have told me that this is the hardest type of problem that we have done that we will do in the entire course. It can be confusing, so we'll go through it slowly, step by step, and see if we can figure out what's going on as we go along, what's going on as we move forward.